Hello everyone, and welcome back to our discussion on the principles of bonds. Today we're going to be continuing that discussion and discuss some of the basic modifications that one could impose on a financial product of a bond. Now, before we get into those little details, I just want to do a brief overview of the principles that we discussed last time. So let's assume that we have a bond. So what exactly is a bond? A bond is where you lend somebody some money and then they give you an IOU. So in this particular case, the amount of money that we're lending out, F, the face value or par value, is going to be $700. So we're going to lend somebody $700 at time t is equal to 0. And then at time t is equal to 1, 2, 3, all the way up to n minus 1 and n. We're going to be getting these coupon payments in the amount of C. Potentially different, but in this case we're going to assume that those are fixed. That coupon rate is going to be 1.1% of the face value of 700. So what will that be? So that means our coupon payments will be equal to, generally speaking, RC times R, which is going to be equal to 0.011 multiplied by our 700, and that's going to come out to approximately $7.70. In addition to these coupon payments, we're also going to get a redemption payment at time t is equal to n, and in this particular case, then that redemption payment is going to be in the amount of $700 as well. So each of these C's are 770, and then at time t is equal to n, we're going to get 770 in addition to 700, so $707.70 at time t is equal to n, where n in this case is going to be equal to 12, which is going to represent, let's say, monthly payments. So that would be a bond whose maturity is 1 year. So here is this financial product, and the first question that we might want to ask ourselves is the following: should we buy this? And if we do buy it, does buying at any price P that is less than the face value F a good choice? Is that always a good choice? As long as P is less than F, in this case $700, is that always a good choice or a good investment for us? Take a guess, pause the video, think about it. But the answer is not necessarily. Not necessarily, so you have to be very careful with that. So let's assume that the monthly effective interest rate I is equal to 1.3%. So what will be the present book value under I at time t is equal to 0? So generally speaking, that's always going to be equal to the coupon payments, C, or sometimes people will call them the interest payments, times the present value of an annuity immediate, plus R times nu, our periodic discount factor, to the power of m. And using all of our values and formulas that we've previously described, that's going to come out to approximately $684.54. Right? Keep in mind our F was equal to $700, and the present value of the sequence under I is 684. So if we buy above 684, that's obviously going to be equal to, a difference that's negative for us. But if we buy cheaper than 684, we're going to be making at least some profit, right? Because keep in mind, if you buy at $100, you have that $584.54 as a unrealized gain for your financial product, right? So as long as we buy less than $684.54 and these interest rates stay fixed and nothing unexpected happens, then that should be okay. So with this information, let's assume that we buy this bond at a price of $650. So that means we have an unrealized gain of about $34.54. So what would be the yield rate? Right. So let's actually just state that. So our unrealized gain is equal to $34.54. Right. So that's the difference between price and that present day book value under I. So what would be our yield rate? So our yield rate is where you set P equal to the book value under some interest rate J at time t is equal to 0, and solve for J. And keep in mind, as J gets closer to 0, our book value is going to rise. So you set that equal to our value of P, and that's going to give you your J value that we're interested in. And you should realize for this particular example, or find on your own, that J is going to be approximately equal to 1.78%. right? So it's positive. That's great. So everyone should be happy, but of course, if you can purchase this at a price less than $6.50, obviously that yield rate is going to be a little bit more. Now, under this transaction of $650 for our buying price, is our bond a maturity premium bond? So keep in mind, we have to do a little bit of math just to be sure, but the maturity premium, if it is a premium bond, is just going to be equal to BVJ minus our redemption value R. Keep in mind, this is a maturity premium, so it's with respect to the redemption, but if it's a face value premium, then it's with respect to F, not R. So this is going to be equal to what? So since BVJ is simply just going to be equal to P, that means we just need to calculate P minus R. So keep in mind, P is going to be equal to 650 as R is going to be equal to 750. So notice that here we have minus 50. So our maturity premium isn't actually a premium at all. It is a discount. So that means our maturity discount, which generally speaking is defined to be equal to R minus BVJ, at time t is equal to 0. That's obviously going to be equal to $50, right? So that means we bought a bond at a maturity discount, right? Now, could we have found out that this was a maturity discount bond purchase ahead of time? Yes, indeed there is. Keep in mind we have a few formulas that allow us to know that ahead of time. So keep in mind the modified coupon rate, RMC, is defined to be equal to the coupon rate, RC, times the face value divided by the redemption rate, which is equal to 0.01 times 700 divided by 700. Notice that if F is equal to R, that is it's a par value bond, then RCM is just equal to RC, right? So that's just going to be equal to 0.01, which is obviously RC. And that's true for all par value bonds, right? Nice little corollary. And our J value was 0.0178 approximately, right? So if we compare these particular things, we have 0.01 is less than 0.018. So keep in mind, if RCM is less than J, then this is true if and only if this is a maturity discount bond transaction, right? So that's one of the things that we have, and that's an if and only if statement. So RCM less than J if and only if maturity discount bond transaction. Right. Now another thing that some people will consider is the interest payments for us. So the interest payments will be equal to what? So that's obviously equal to N times the number of coupons, or technically speaking, generally, so the sum from, let's do a different subscript since J is already used, the sum from L is equal to 1 to M of CL. So C1 plus C2 plus C3 all the way down to Cn, and this is the generalized version. Generally, for us, since our C came out to 7.70, that's going to be equal to 12 times 7.70, which is going to come out to approximately $92.40. So $92.40 in interest for us, right? So what is this $92.40? So that's all we get until our maturity redemption value. Redemption payment. All right. So here's a question that you should be able to think about. If we change our mind at time t between 0 and n, for whatever reason, should we sell? Should we sell, or should we just be a little bit more patient and wait? So let's actually go ahead and look at that. So if we should sell, we obviously should sell that compared to the book value at whatever time t we are at. So generally speaking, the book value at time t is equal to k under some purchase yield rate J, that's obviously going to be equal to, so now we've gone through our timelines, so 0, 1, 2, all the way up to K, and then K plus 1 all the way up to, say, M minus 1 to M. Why is my dots above? I don't even know. So they should be there. So if we want to find our book value at this particular time, which only considers the rest of the payments because that's what we will sell if we do sell anything, this is just going to be equal to just a shifted or deferred annuity immediate. So C times A, M minus K times J, or of J, and then plus R, our redemption value, times n to the power of N minus K. Right? And this representation obviously should look familiar if you know anything about deferred annuities. So using this relation, we can actually consider the value of our book value at a bunch of times t is equal to k. So BVK under J. So what I want to do is, since we're looking at a year, so let's just partition it into quarters. So 0 months, 3 months, 6 months, 9 months, and 12 months. And then you can just substitute those values of k for our particular n and then calculate. So you might want to pause the video and try and see if you can get these numbers on your own. So this is going to be equal to what? So it's a par value bond. So this is going to be equal to what? So it's going to be equal to 650, which keep in mind was just equal to P, the price we paid at time t is equal to 0. And then as k increases, as time moves forward, is the value of BV going to increase or decrease? Well, you should know that this is going to increase. And if you don't, you can let the math guide your intuition. So 661.53, and then it's going to go up to 673.69, and then it's going to go up to 686.50. And do you know what it's going to go up to at time t is equal to m? This is going to go up to $700, which is who? Do you know what's so special about this 700? That is equal to our redemption value. And I suggest you try and prove this analytically. Prove this on your own, that the book value under some yield rate J at time t is equal to n will always be equal to r. Okay? So from this little table, what can we conclude? So as t gets closer to n, we will soon get to a book value of r. So increase your selling price towards P, the price for which you originally bought this bond at. And keep in mind, you might want to pause and think about this for a moment as to why this is, because if we're going to be selling our bond, our goal is to sell it for at least or somewhere around the amount for which we lost in the first place. So we purchased the bond for $650, right? And, you know, working out those things, you can calculate the present value with respect to the remaining things, which is $700 plus the remaining coupon payments, right? So obviously it's going to be worth around $700 the closer and closer you get to time t is equal to m. But if you want to sell it extremely quickly, you obviously need to sell it at a discount, something lower than $650. But as t gets closer and closer to n, you might as well wait, because eventually your selling price is going to be equal to p, then you're going to break even and you're going to be losing out on that $700 that you're about to get. So if you do not increase it towards p, or at most $700, because obviously you can't sell this bond at more than $700 or extremely more than $700, because those coupon payments are barely nothing, because they're only going to get $700 back. So selling it more than $700 substantially is definitely not good for the person who's about to buy this loan from you. Now that we know the basics of the mathematics associated to bonds and pricing bonds, let's try and generalize things as much as we can before things get too complex. So we've obviously assumed under the previous formulas that the interest rate has been fixed. That's rarely ever the case, so that's going to be the first thing that I'm going to change here. So we're going to have an effective interest rate at time t is equal to 1 of I1, and then I2, then I3, and then I4, all the way down to IM minus 1 and IN. So we obviously have variable interest rates. And we're also going to have potentially changing coupon payments. Let's call them C1, C2, C3, C4, all the way down to Cn minus 1 and Cm. And obviously we're going to have our redemption payment at time t is equal to n. You could also have some other redemption payments before t is equal to n, but that's rarely ever the case, so I'm not going to mention it here. But the mathematics will sort of follow the same exact discussion like we did with drop payments and balloon payments. So now that we have these variable interest rates, let's just remind ourselves a couple notations here. So let's just remind ourselves. So alpha k is going to be defined to be equal to 1 plus ik, and nu k will be defined to be equal to 1 over 1 plus ik. So that is your variable accumulation factor and your variable discount factor. So if we look at a particular timeline where this is time t is equal to k minus 1 and time t is equal to k, to get from k minus 1 to k, that's going to be under alpha k, and to go from k to k minus 1, so backwards in time, that's going to be equal to nu k. So from an equation perspective, from accumulated perspectives, sk will be equal to sk minus 1 times alpha k, and then sk minus 1 will be equal to sk multiplied by nu k. Right? So all of those things are going to be equivalent. So we have variable coupon payments and variable interest rates. So how are we going to find the book value under this particular structure? So one way you could do it is using direct rates, which I'm going to superscript with d, at time t is equal to 0 under interest rates ik. So that's going to be equal to the sum from k is equal to, usually we don't start at 0, but I guess you could have a coupon payment today. It doesn't really make much sense, so let's just go to k is equal to 1 to the power of n, ck divided by 1 plus ik to the power of n, and then plus r all over 1 plus in to the power of m. All right, so this is direct rates. Right? Now keep in mind, what is this direct rate? So what we're doing here, if we've got 0, 1, 2, 3, 4, for example, we have this C4 payment here, what I'm doing is I'm discounting it backwards by V4 to the power of 4. Right? But keep in mind, interest rates might change on the intermittent values, but I'm pretty much using I4 as a representative for all of 0 through 4. When in reality, I4 only cares about I3 to I4. So it's very easy to see that this is not very accurate in practice. It's not very accurate in practice. But what we can do is we can use all rates in between. So we're going to represent this as BV0IKS, where we're going to use every rate simultaneously or sequentially with respect to each other. So this is going to be equal to the sum. Actually, I'm not going to write it as a sum quite yet. So what are we going to have? So we have our C1, we have our C2, we have our C3, and so on. So C1 is going to be discounted by nu1. C2 is going to be discounted by nu2 followed by nu1. And then we're going to have C3, which is nu3, nu2, nu1. And then that's going to go all the way down to what? Our last one, Cm, which is nu(n), nu(m) minus 1, all the way down to nu1. And then we're going to have plus r, nu(n), nu(m) minus 1, all the way down to nu1. Now, that notation is obviously a little bit more complicated than I want to deal with. So what we're going to do is we're just going to create some new notation here. We're going to denote capital PK to be equal to the product nu1, nu2, all the way down to nu k. So this is just going to be a product, a product of news. So therefore, I'm just going to take that representation. I'm going to take that representation. So therefore, BV0IK S is going to be equal to C1 pi 1 plus C2 pi 2 all the way down to Cn pi n plus R pi m. And now you're like, oh, it's actually very easy to write in summation notation, and you would be right. So BV0IK S will be equal to the sum from k is equal to 1 to n of ck pi k n plus r pi n. And again, this is called the simultaneous rate approach for defining book values. And what's the advantage here? Obviously, this is accurate, but hard to calculate, because we need every single nu1, nu2, nu3, nu4, especially if this is a long bond, like a 3-year bond, we need 36 values of mu, right? 36 different interest rates. And it might change a lot, so maybe this calculation is very sensitive to spikes in the process. So an alternative that you could do, alternatively, right, and this follows the same exact narrative as we did with variable interest rates, we can approximate IK on t from 0 to n so we're approximating the interest rates. Technically that would be a plural. All of them on 0 to n, so 0 to 1, 1 to 2, 2 to 3, 2 to 4, all the way down to n minus 1 to m. We're going to approximate all of them with a single rate Sn. And this Sn is referred to as a spot rate. So how are we going to approximate a bunch of interest rates with a spot rate? Well, a couple common ways you could do it is the following. So we could do, for example, the arithmetic average of the interest rates or the geometric average of the interest rates on the interval 0 to n, and use them and approximate Sn with either or other ones, right? And in case you don't remember arithmetic and geometric means, the arithmetic mean of the interest rates is I1 plus I2 all the way down to Im all divided by n, and the geometric one is going to be the nth root of I1 times I2 all the way down to Im, right? So that's the arithmetic and geometric mean approximations. So once we have these spot rates, then we can define our book value at time t is equal to 0 with interest rates IK approximated via spot rates via the sum from k is equal to 1 to m. And this is going to look very similar to the direct rate, but direct rates are not very useful. And instead of IK, we're just going to be using SK. So that's going to be SK to the power of k, and then finally R all over 1 plus Sn to the power of m. Right, and that should be lowercase letter m. Right? So that's going to be the spot rate approach for calculating book values, right? So we have direct rates, sequential rates, and also spot rate approximations for the book value at time t is equal to 0. And obviously you should be able to turn all of these formulas from BV0 into BVK, where k ranges from 0 to n. So the generalized book value at any time k, but the formulas, just mostly change the subscript on each of these statements. Now let's talk about a couple important concepts associated to bonds. With bonds, keep in mind you can always sell them, provided you can find someone to buy it, right? This is a very, very, very big if. Because if people don't have a lot of money, they can't buy anything. And if people have a lot of money, they could be very conservative in their spending at the time for which you want to sell. So with bonds, it is potentially risky. it is potentially risky to sell, but keep in mind the return, the maturity, redemption value will not change. So it's not risky on the financial part, but it's risky if you want to sell it or liquidate it extremely fast. So let's consider this scenario. You own a bond and interest rates go down before maturity. Let's go down before maturity. So what type of things would you expect? So the first thing will be as follows. So your bond will likely have higher coupon payments than bonds issued under the lower rates, right? Because if all the interest rates go down, that means the interest rate payments will also be lower as well. So that means if you sell your bond now, if you're able to at least, then your bond will actually have a higher value than those in the present time because they're going to be paying more periodically, right? So if this is the case, then this will allow you, most of the time, you to, let's actually say that, potentially, sell your bond at a profit, or technically speaking, a premium, right? So what are you going to do with that profit in premium? Well, obviously you would take the profit and reinvest, right, into something that, is going to make you more money over that term. But keep in mind, since this bond has higher coupons, you should be able to sell it a lot more than you should have before, right? So reinvest that into a high yield savings account so that you can make at least the amount that you would have made under the coupon payments of the bond that you're about to or considering to sell. Another bit of terminology that's often used with bonds is the terms callable and non-callable bonds. So what we've been discussing up to this point is referred to as non-callable bonds, which are bonds for which the issuer does not give the bondholder the option. An option is a very commonly used word in the realm of finance, to retire the bond prematurely. Therefore, you can't be like, oh, I want to sell my bond today, but I can't find anyone to buy it. Can you give me the redemption value today or a small percentage of that? They are not entitled to that reimbursement prematurely. So if interest rates go down, then the bondholder has to find their own person to buy it, right? And that can be extremely annoying. Maybe you need that money at that time, or maybe a percentage of that redemption value. Now, technically speaking, all bonds are callable at time t is equal to n. Because at time t is equal to n, you say, hey, my bond is over, can you give me back my redemption values? And they usually, technically have to say yes, else they have to deal with some legal things, which I'm not going to get into today. So this is what we refer to as a non-callable bond. That is, you cannot back out of this contract prematurely. So the opposite of a non-callable bond obviously is going to be a callable bond. So what is a callable bond? So a callable bond, take a guess of what a callable bond is it's a bond that allows the bondholder to call, finance term, their bond early at times typically pre-decided by the issuer, right? So these call times, so let's actually draw a timeline to sort of draw this out before we start talking about it. So here's our timeline: 0, 1, 2, 3, 4, 5, 6, and 7. Let's assume that n is the original maturity time. And let's assume that this bond has these call times already decided. Let's assume that the call times are 2, 4, and by default, 7. So I'm going to call these times tcall, which is going to be at these times t1, t2, and t3. So there's 3 call times, the last being the default. Some people will leave that out, but it's technically speaking should be there, which in this case is going to be equal to 2, 4, and 7, which is technically going to be equal to m. And let's assume that we have coupon payments scattered throughout this bond. Let's assume that they're fixed. Let's assume we have coupon payments 5, 5, 5, 5, 5, 5, and 5. And let's assume that the redemption value is 150. So if the redemption value is 150, do you think that the bond issuer should give back 150 at time t is equal to 2 and 4? Obviously no, it should be less. So by how much? Well, this is another technical question, but let's assume that this value at time t is equal to 2 is $20, and let's assume at time t is equal to 4 it's $45. Right? So those are the redemption values at the call times. So the redemption at the call times, I'm going to denote by W1, W2, and W3. And in this case, this is going to be equal to 20, 45, and 150. And obviously 150 is equal to R. Right? So this is what we refer to as a callable bond. So if you purchase the bond at time t is equal to 0, you have to wait until at least t is equal to 2 to call it. But once you get to t is equal to 3, you can't call it. You have to wait until 4. And if you get to 4, then you can get your 45 partial redemption value or your callable redemption value. And if you do not call at time t is equal to 4, you cannot call until maturity at time t is equal to n. Right? So that's what a callable bond is. So let's now talk a couple of strategies. So when to call, and some people also say withdraw from the bond. Right? So a couple important points. Issuers, the people we lend money to, prefer bonds with a lower book value. Now think about that. Why would issuers prefer bonds with a lower book value? Well, one obvious reason is that they owe less to the lenders, which is us. Also, they prefer lenders to call. So what do you think? Do you think an issuer prefers you to call at time t is equal to 2, 4, or 7? The general case is that they prefer you to call early. And think about that. Why do you call early? So why? Well, one obvious reason is because the book value gets closer to R as t gets closer to m. And we prefer lower book value. So using that sequence of logic, that means we prefer our lenders to call early. That's when our book value is less, because as t gets closer to n, BV gets closer to R, right? It increases to R, which they do not want. So in continuation, what does that mean? So they prefer us to call. So at which time is ideal for them? They obviously want us to call at time t is equal to the minimum of t call. So for our example, that was t is equal to 2. And this sequence only makes sense if our CKs are too much or too expensive. So they're giving us really high coupons. They want us to back out as soon as possible because they're losing too much money, or maybe that's cutting into their profit margins, or maybe they're not making any money at all and they're actually at a loss because they have to pay us these coupon payments. That's another reason why zero coupon bonds are a thing, because then they don't have to deal with, oh, the CK is too large or too small. right? So another perspective, so if the CK is too little, zero coupon bonds are obviously the more ideal case for this, then what do they prefer? So issuers prefer us to call at time, take a guess, at time t is equal to the maximum of t call, which usually is equal to n, right? So what's going on here in terms of premium and discount bonds? So obviously this category above would be selling at a premium because, you know, it has high coupons, and obviously this case will be selling at a discount most of the time anyway. So one last formula, and that pretty much wraps things up. So let's actually suppose that NW, that's a W, even though it doesn't look like it. So NW is equal to the number of payments until we call, right? Which, keep in mind, 0 less than or equal to NW less than or equal to M. So when we call, some people will actually price things with respect to NW, not M, right? So how to price with respect to NW, not M. Well, typically, so before, recall that P was equal to C times ANJ plus R nu j to the power of n, right? And if we look at our timeline, we have 0, 1, 2, all the way down to m. But now we have this new time over here, nw. We want to call for whatever reason, right? Interest rates go down, and we want to just sell this bond and make some profits elsewhere, right? So in this particular scenario, this phase of the bond is not for us, right? Because we're going to call here, provided that we can. So we only have NW payments that we need to price with respect to, right? Because you're not going to be selling the bond, because you should be selling bonds with respect to NW, because if you sell it, they're probably going to sell it also at NW or call it at that particular point. So everything will be overvalued if you price it with respect to N and not NW. So this is kind of one of the reasons why you want to price with respect to NW and not N. So that price with respect to call, some people will call this the call pricing of the bond, or the call book value. And this is going to be equal to C, our coupon payments, provided that they're fixed, but they don't need to be. And then this is going to be A and W under J, and then plus W times nu J N W. So that would be our value, where our coupon payments are C, 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 and W is the amount for which you pay at time t is equal to NW. Right? So those are some of the basic modifications that you can impose on types of bonds, and also some modifications on how to price bonds as well, both in the callable form and also the non-callable form as well. So I hope you enjoyed this video, and I'll see you in the next one. Take care.